The three resistors, they are connected in series. So their equivalent resistance Rs is equal to R1 plus R2 plus R3 and is equal to 9.00 ohms. We apply Ohm's law to the equivalent circuit. It means we want to find the total current passing through all the three resistors. So I equal to V over R and is equal to 18 over 9 ohm, and it is equal to 2.00 ampere. Next, we want to calculate the potential difference across each resistor. So V1, so this is V1 and this is V2 and this is V3. V1, we apply Ohm's law again, IR1, and you will find this equal to 8.00 volt. V2 IR2, which is equal to 2.00 volt. V3 IR3, and you will find this is 8 volt again. Let's calculate the power. The power is equal to P equal to VI. So the power dissipated on the first resistor P1 equal to V1 multiplied I. I is the same for all three resistors. So this is 8.00 times 2.00 and it is 6.00 watt. P2 V2I and 2.00 equal to 4.00 watt. P3 V3I, this is 8.00 2.00 and this is 16.00 watt. The power supplied by the battery P supply is equal to VI again, and the potential difference or the EMF of the battery is 18, and the current again is 2, so this is 36.00 watt. Now if we sum all the power dissipate on each resistor, so you will find this also equal to 36 watt. So they are equal. In this circuit, all resistors, they are connected in series, so their equivalent resistance is just the sum of all resistors. Rs equal to R1 plus R2 plus R3 plus R4 and plus R5, and the result will be 60 kilo ohms. So we can redraw the circuit. Since the battery opposite to each other, so we can say the 24 volt battery will provide a larger EMF and drive the current through here. We can draw a KVL loop. So from here we can have positive negative, this is positive, negative, and when the current goes back to the 24-volt battery, this is negative and positive. Let's start from the equivalent resistor first. Now, we don't know the voltage across the resistor. However, we can assume the current is I. So we can say positive 60K. Here, I don't put ohm here because ohm is the unit. I just put the prefix 60K. It means 60 times 10 to the power 3. This is the number. Multiply I. I is the current. So this factor here is the voltage across the equivalent resistor. For the 12 volt, which is positive 12, and when you reach here, it will be then negative. So negative 24. After a complete loop, this equal to 0. So 60K I equal to 12, and I equal to 12 over 60K. One thing about this sort of expression is when we have K as 1 over K, remember K here means 10 to the power 3. So you are talking about 1 over 10 to the power 3, and this is 10 to the minus 3, and it means this is mini in terms of the prefix. So the rule is whenever you see 1 over K, you convert this one into mini. And you can use your calculator and find 12 divided by 60. And you will find the answer is 0.2. And then 1 over K is mini. And I put the unit now. The unit is ampere. So M. So it's 0.2 milliamp. Let's look at the voltage across each resistor. V1 is IR1, and you will find this equal to 2 volt. V2 IR2, and this is equal to 4 volt. V3, this is IR3 equal to 2 volt. V4 IR4, this is equal to 2 volt. V5 IR5, this is equal to 2 volt. Now let's look at the power dissipate on each resistor. P1 is equal to V1 I. So this is equal to 0.4 milliwatt. P2 the same, V2 I, and this is equal to 0.8 milliwatt. P3 the same as P1, so it's 0.4 milliwatt. P4 0.4 milliwatt, because they all have the same voltage and the same current. Next, let's calculate how much power all the resistors consume together. So 0.4 milliwatt plus 0.8 milliwatt plus 3 times 0.4 milliwatt, and you will find this is equal to 2.4 milliwatt. Now let's calculate the power supply or absorbed by each battery. So first look at here. The power on V2, it is delivered because the current drive from the positive direction to the outside circuit. So this one, P2, is supply. So this one will be V2I equal to 24 times 0.2 times 10 to the minus 3 watt, and it is equal to 4.8 milliwatt. However, the power on the first battery, because the current is entering from the positive side, so the power actually absorbed by the first battery. So P1 V1I and is equal to 2.4. So this is 2.4 milliwatt. Now let's look at the total balance. The power supplied by V2, the second battery, it is 4.8 milliwatt. This is equal to the total power dissipated on the resistors, and this is equal to 2.4 milliwatt plus the power absorbed by the first battery, and this is 2.4 milliwatt. So they are balanced. Now let's apply Kirchhoff voltage law to two loops. First, we have to mark the voltage. The voltage across resistor R1 is 6 volts. The voltage across R2 is V2. The voltage across R3 is V3. Now we have to draw the two KVL loops. First, I draw the first loop. I call it loop 1, and I draw it counterclockwise. I also draw the second loop counterclockwise, loop 2. Let's travel along the loop and see how the voltage will be. Say, assume we first travel to the battery. Battery here is negative. So when the path or when the loop meets the battery, it is negative voltage. When the loop meets the first resistor, this should be positive. It means the voltage this side of the resistor is higher than the voltage of the other side. So it's from positive to negative. This is so-called engineering convention. When the loop passes through R3, the same argument, it has to be positive to negative. Now we write down the KVL equation for the first loop. Loop 1, we apply KVL. So we first meet the negative 18 volt. Now I won't put the unit here because I understand I'm writing an equation in volt. Next is R1. Here we meet the R1 at the positive side, so it will be positive 6 volts. Next is the V3, so it is positive V3, and because the loop is complete, so it must equal to 0. From here we can tell V3 is equal to 12. Now I put the unit, which is volt. Let's look at loop 2. Let's analyze again. We can start from the battery. When the loop starts from the battery, it will first meet negative sign of the battery. So the battery should be negative 20. Next, when the loop passes through R3, we already say this side is negative, so it will be negative here. When the loop passes R2, we assume this is positive, and this, so therefore the V2 is positive. So we put all this together, and we are going to write for loop 2 is KVL equation. The first, the battery, which is negative 20. So negative 20, and then negative here V3. We just found V3 is equal to 12 volt. Again, I will skip the unit when I write down the KVL equation. Next is positive V2 equal to 0. So V2 equal to 32 volt. Now let's put down all the voltage and see if they are agree with our calculation. Let's check. So this is 18 volt, so we assume this is 0 volt, so same as this one, 0 volt, 0 volt. From 0 across the battery, so this point here should be 18 volt. The potential difference across R1 is 6 volt. So this is the potential difference across R1, and the potential will drop across R1. So this will be 12 volt. So from here to here, it is 6 volt. And also from this point to here across R3, it will be 12 volt, and this is what we calculate here, 12 volt. If we look at this point, this is 0 volt, but this is 20 volt. So this is positive, so the other side must be negative 20 volt. So now let's check. From this point, 12 volt point, to this point, if you look at it, the potential difference is 32 volt, and this is what we calculate, V2. So V2 is 32 volt. This question is exactly the same as last one, except the polarity of E2 is swapped. So now we have positive here instead of negative. Now let's mark the voltage across each resistor. This is 6 volt. V2 across R2. V3, this is the potential difference across R3. Now I will draw the two loops, and I will draw them counterclockwise. Loop number 1, loop number 2. If I follow the path of the loop, loop 1, it will first encounter the battery in the negative side, so the battery is negative 18, and then it will go to R1 and it will be positive and when loop 1 pass through R3 is also positive. This is our assumption. So now I write down the KVL equation for loop 1. First, the battery is 18 volt. Again, I skip the unit. Next is the voltage across R1, which is positive 6. And then when the path across R3, it will be positive V3 and equal to 0. Now V3 again, it is equal to 12 volt. Next, let's look at loop 2. This time, when the path enter the battery, which is positive, and when the path enter R3, it will enter from the negative potential side. And when the path enter R2, we can assume again this is positive. So we have positive, negative, and positive. Let's write down the KVL equation for loop 2. KVL, starting from the battery, positive 20. And then the voltage across R3, so it is negative. We know that R3 will be 12 volt, so I can put 12 here. Next is the voltage across R2 with the engineering convention, and we assume this is positive, so we call this V2 equal to 0. Now we can solve this equation, and we'll find V2 is equal to negative 8 volt. Now let's put all the value and see if they are consistent with the given voltage. Again, for the first E1, which is 18 volt, we assume this is 0 volt. This is also 0. This is also 0. So at this point, it will be 18 volt. We know the voltage across R1, which is 6 volt. And so from the 18 to here, it will be 6 volt potential drop, and this is 12 volt at this point. So it also consistent with V3, because from here to here is again 12 volt, and this is V3, and this is what we just calculated. Now let's look at the battery, the other side. This is 0, so here should be positive 20 volt. Now in terms of potential difference, we should put it here. And remember, we assume in the beginning this is positive and this is negative, and then we find the voltage V2 is negative 8 volt, which is consistent. So in reality, we can put it this way. We can say this is actually positive, this is negative. And the potential difference, if I put it more precisely, the delta V between the positive to the negative is equal to 8 volt. So this is the real voltage, or in terms of the calculation, our calculation will show V equal to negative 8 volt, because when we make the assumption about the voltage across R2, we assume positive and this side is negative. But in reality, we should swap it. This circuit is very similar to the last two. However, it's more difficult and challenging. First, we don't know the power. First, we don't know the voltage of the two sources. So we need to find E1 and E2. We are not given any voltage across the resistor. Instead, we know the value of the resistance. So R1, the value is 2k ohm. R2, it is 3k ohms. R3, the value is 1k ohm. Let's look at the current. Now, there is a note here. So we assume the current starts from E1. So we first draw the loop. This is the first loop, and the current starts from E1. So this is start from positive, and across R1 this is positive, this is negative. We assume the current going through from the top to the bottom. So across R3 this is positive and this is negative. Now the current at here will branch out. So if I put this one as I1, the current passing through R1, or we assume this I1 splits into two paths. One is I3, which is the current passing through resistor 3, and I2, the current passes through resistor R2. Now we have a note here, so we will apply KCL, Kirchhoff current rule, on this point. Next, we draw another loop on the right hand side. We also do it clockwise. So this is loop 2. Kirchhoff current rule say the current in is equal to the sum of the current out. So I1 must equal to I2 plus I3. Now we are also given I1 is equal to 6 milliamp. So this is 6 milliamp. And I2 is 4 milliamp. So this is 4 milliamp. So now we can calculate I3. I3, the current passes through the resistor 3, is equal to I1 minus I2, and is equal to 6 milliamp minus 4 milliamp, and is equal to 2 milliamp. Now we are going to apply the KVL across the component around the loop 1. So loop 1, we apply KVL. This path we choose is clockwise. Again, it doesn't matter we choose clockwise or anti-clockwise, because all the sign will be reversed. So in this case, I just chose clockwise. This is the direction of the path, and this is negative. So we'll say this is negative E1. Next, the path enter R1 from the positive sign. This is our assumption. This is positive. Now, we don't know the voltage across R1. Now remember, we need to put down the voltage across R1. However, we do know the current and the resistance. So we can use Ohm's law remember what Ohm's law say? Ohm's law say V equal to IR. So we'll put a bracket. So we know within the bracket, this should be the voltage across R1. First is the I. I is 6 M. Again, I don't put the unit here, but I make sure I will keep the prefix, which is 10 to the minus 3 or M. Multiply the resistance, which is 2 kilo ohm. Again, I don't write the ohm here. I just put 2K. K is a prefix, mean 10 to the power 3. So this is 2K. So the value within the bracket is the voltage across R1 plus I3. So I3 is equal to 2 milliamp when the path enter R3 is enter from the positive side. So we put positive here. Bracket, this is the voltage across R3. The voltage can be written using Ohm's law, which is IR. I is the I3, so it's 2M. We just calculate here. I3 equal to 2 milliamp. Multiply the value of R3, and it is equal to 1K. So the loop is complete and equal to 0. Now, one thing about this way is, if you look at M here, M is equal to 10 to the minus 3, K equals to 10 to the power 3. So they equal to 1. So there's a rule. Whenever you have the prefix M multiply the prefix K, it's just equal to 1. So here it becomes minus E1, 6 times 2, which is 12. Remember the 12 mean volt, but I just skip the unit volt. Plus 2 times 1, 2 equal to 0. So E1 equal to 14. Now I put the unit volt. Let's look at loop 2. Loop 2, if we start again from the battery or E2, the power source, it will enter negative first. So negative E2 again. When the path transfer or enter R3, it will enter from the negative side. So this is also negative. When the path passing through R2, we assume it's from positive to negative. So we put everything together. Loop 2, we set up the KVL. The first, negative E2. I put negative E2. Second, negative the voltage across R3. So I put a bracket, so I know I'm going to put the voltage, but I don't know the voltage, so I can express the voltage in terms of IR, use Ohm's law. The I is equal to I3. I put it a little bit later, and the resistance is 1K. Next, this is R2. So the R2 here is positive. I2, the resistance is 3K equal to 0. It becomes E2 minus 2M. I3 equal to 2 milliamp. Multiply 1K plus I2 is equal to 4 milliamp. So this is 4M. multiply 3k, so equal to 0. Again, we use the rule whenever we see 10 to the minus 3 it means mini multiply 10 to the power 3 is equal to 1. So we just look at the number 2 and 1, we just multiply them. Minus E2 minus 2 plus 12. So E2 equal to 10 volt. Again, this is the same circuit, but the value we are given are different. Let's look at R1 is given as 2 kilo ohm, R2 3 kilo ohm, R3 1 kilo ohm. E1 is given as 10 volt. This is E1. E2 we need to find out. Here, let's look at the node at this point. Again, this is I1, the current passing through R1. This is I2. We assume this current will split into I2, and this is I3. This is our assumption. In this circuit, we know the value of I1 is 6 milliamp, but we don't know I2 or I3. Now, let's first write down the KCL at the node. So we'll say KCL, and the current in equal to the current out. So I1 equal to I2 plus I3. Now we know I1 is 6 milliamp, so we can say 6 amp equal to I2 plus I3. Now this time we don't know I2 and I3, so we cannot use KCL to solve both. So we need KVL. Let's draw the KVL loop. The first one here, again we draw it in a clockwise. This is loop 1. This loop or this path, when they enter E1, it will enter from the negative side. And when they enter R1, it enter from the positive side. When you assume it enter R3, also from the positive side. So now we write down the voltage across the loop 1. So KVL loop 1. Start from the battery. We have negative 10. Again, I skip the unit, just put 10, but I know this is voltage. Next, the voltage across R1. We know it enter R1 from the positive side, so I put positive here. But I don't know the voltage, so I put a bracket here. I can write the voltage, use Ohm's law, V equal to IR. I want to know the current passing through R1, and I know this is 6 milliamp, so I put 6 amp. R1, 2 kilo ohm, so I put 2K. This is the voltage across R1. Next, plus. Again, I assume the current from the positive side, or the loop enter R3 from the positive side. So this one, I put a bracket here. The current is I3. I don't know I3, so I just put I3 here. And I can put the resistance of R3 here. So this is 1K. Now this loop 1 is now complete and must equal to 0 according to the KVL. Let's simplify this one. We use the same trick. When we see M and K, we can just say they become 1. So we just focus on 6 and 2. Minus 10 plus 12 plus, I keep the K here, 1K I3 equal to 0. So 1K I3 should equal to minus 2. What I mean is I3 equal to negative 2 over 1K. Now 1 over K is mini, so this become minus 2 mini M. Now remember, this is interesting. We're seeing the sign here is negative. So if we look at our circuit, we assume I3 coming from the top to the bottom. With this assumption, we find that I3 actually is a negative. So what I mean is our assumption was not correct. But I'm better keep this one here, and we later will fix everything. So next, we're going to look at the KVL of the right hand side. So I will put draw another loop. This is my loop 2. Now I will do it step by step. Assume I don't know the value of I3. I just follow the assumption. So this path or this loop will first enter E2 from the negative side. So this is negative E2. And then it enter R3 from the negative side. This is what we assume. So we still keep our assumption here. It enter R2 from the positive side. So let's put down all the voltage carefully. So if you look at KVL for loop 2, so negative E2, and then negative, so we put the negative here, bracket, this is the voltage. Now this voltage is equal to I3 multiply the value of R3, 1K, plus bracket, and the voltage across R2 is I2 multiply 3K, and here it is equal to 0. Now before we look at this one, let's see. We already know I3. So we know I3 is negative minus 2 milliamp. But this equation, we still need to find out E2 and I2. But we can use the KCL we written down earlier. So what we can do is we can first find I2 from the KCL. So let's go back here. The KCL say 6M equal to I2 plus bracket I3. Remember, the bracket is important because I3 is negative 2M. So now I2 equal to 8 milliamp. Now we plug this number in, minus E2 minus, remember I3 numerically, we find this is negative 2m multiply 1k. Keep all the sign times 3k. And beg your pardon, I2 is 8m. So minus E2, this is plus 2 volt plus 24 equal to 0. Therefore, E2 equal to positive 26 volt. Now let's put everything together and see if they are consistent. So what we found first, I3 is a negative value, so we should withdraw this one, and this will be here, I3. So physically, the I3 is from the bottom of the circuit to the top, and also the assumption we make about positive and negative should be reversed. Okay, so this is 26 volt. Okay, and now we can calculate the voltage at the junction and see whether they are consistent with the whole circuit. The voltage across R1, we call it V1, is equal to 12 volt. Okay, so if this is 10 volt coming from here, and remember we assume I1 passing through here, so this point must be minus 2 volt. Okay, and if this we assume 0 volt, this is 0 volt, and this is 0 volt. This is minus 26 volt because the battery is 26 volt. Now let's see the voltage across R2. The voltage across R2 is equal to V2, and is equal to I2 R2. I2 is A, so it's 24 volt. So yes, it agrees. So this is 24 volt, the potential difference. If you look at minus 2 this point, minus 26 this point, so yes, the current I2 will flow from the minus 2 to minus 26, and the potential difference is 24 volt. So everything, all the value, they are consistent. The circuit of this question is same as the last one. However, we are given a different value for different component. Let's see. R1, it is 2 kilo ohm. R2, 3 kilo ohms. R3, 1 kilo ohms. E1, which is 14 volt. E2, this is 10 volt. Now again, we can assume the current passing through R1 is I1. And we also assume at this junction, the I1 split into two paths, I2 and I3. So we first look at this junction and write down the KCL. I1 is equal to I2 plus I3. Remember, it is our assumption, so we have to find another two equations. The first equation comes from loop 1. So we have to use KVL to write down the voltage across loop 1. Again, when the path enter E1, it will enter negative sign, and here it will be positive, and here of course positive as well. So we are going to write down the first equation for loop 1, KVL loop 1, and this is minus 14 plus bracket, this is the voltage across R1, and we don't know the value, so we can say express the voltage with Ohm's law, V equal to IR. So this time I put the I1 here because it is the unknown, and this is 2K. Now plus again the voltage across R3. I don't know I3, so I put the I3 as the unknown, and then this is 1K equal to 0. Next we look at another loop. Again I draw loop 2, and this is clockwise as well. Same as previous one. When loop 2 passes through E1, it enters from the negative side, and we passes through R3, it enters again from the negative side, and we assume this is positive for the R when they enter R2, and this is negative. So loop 2 for the battery is negative 10. Here is negative the potential across R3. So bracket, the potential across R3 is equal to I3, and this is 1K plus the potential. Why plus? Because it enter this time from positive of the R2. So plus, this is 3K I2 equal to 0. Now basically we have three equations, three unknown: equation 1, equation 2, and equation 3. We can solve this equation and see what value we have. There are different methods you can use. I will going to show you how to use substitution and elimination and combine these two methods together. If you know matrix, you can also use matrix or determinant to solve these equations. So I will say from 1, I will express I3 equal to I1 minus I2, and then I will substitute I3 into equation 2 and equation 3. So I will substitute I3 into 2. Now if I substitute I3 into 2, and also I notice this is negative 14, I'm going to move the negative 14 to the right hand side and become positive 14. So I do it together. 2K I1 plus 1K. Now I3, I'm substitute I3, so I bracket, make sure this is important, I1 minus I2, and equal to, remember, move the 14 to here, so this is 14 positive. Now I will tidy up this one, and this will become 3K I1 minus 1k I2 equal to 14. Next, I substitute I3 into equation 3. I do the same trick. I will move the 10 to the other side. And just be careful. Minus 1k I3 is equal to I1 minus I2 plus 3k I2 equal to 10. Now I'm going to write I1 and then I2 minus 1k I1 minus 1 minus 1. So this is positive 1k. So this becomes positive 4k I2 equal to 10. So now we have another equation which is simpler. This is 4 and this is 5. Okay. Next, I'm going to divide equation 4 and equation 5 by 1000 times. So I can tidy up this one, and this one will become, the 4 will become 3i1 minus I2, 14 divided by 1000, so this is 14m, m means 10 to the minus 3. So this will become still about 4. I keep it here. And this is minus 1 plus 4i2. So this is 10m and this is 5. Now I can say 4 plus 3 times 5. And this I1 eliminate, and this one is minus 1 plus 12 I2 14 plus 30. So I have 11 I2 and 44. Remember you got the m here, 44m. So I2 is 4 milli-am. So we can look at I3 or I1 first. Substitute I2 into 5 minus I1 equal to plus 4 multiplied by 4m equal to 10m. So this one will become 6m A. And of course I3, we go back to this equation. I3 equal to I1 minus I2. So this is 6 minus 4, so equal to 2 milli-am. Now again we can check the potential. Let's look at I1. I1 is 6 milli-am. So I1 6 milli-am. So the potential difference here is 6 milli-am times 2k ohm. Again, the m and the k equal to 1, so it's a 12 volt. So this is 12 volt here. What I mean is, if this is 14 here, because this is 14 volt, this will be 14 volt at this point. So this one is 12, so this should be 2 volt. Now we can verify this, of course. Now I2, let's look at V2. So this, we just calculate V1. Okay, we look at V2 here. V2 is I2 multiply R2. I2 is here, and R2 is 3, 4. So this is 12. So this one is 12 volt again. Now let's check if this is 14 E1. So assume this is 0 volt. This is 0 volt. Okay, so this is 0 volt. This, however, this is positive 10 volt E2. So this point here must be negative 10 volt. So it agree. So from the 2 to negative 10. So we agree. Now we also can check V3. V3 is I3. We use the value we got I, which is 2 milliamp. 2M multiply 1K. So this is 2 volt. And this is exactly what we expect here. This is 2 volt. So they are all consistent. In this question, we are going to find the equivalent resistance of this rather complicated circuit. First, I want to review the rule of how to combine the resistor which they are in series and in parallel. If we have two resistors, R1, R2, if they are connected in series, we can just say R1 plus R2 equal to R series. Sometimes we will see people say RE or EQ. It means the same. EQ means equivalent. Now, if you have two resistors, they are connected in parallel, R1, R2. It means I want to find one resistor. Replace these two. So I will say this RP, resistor in parallel. The way to calculate is 1 over RP equal to 1 over R1 plus 1 over R2. Or you can simplify this as 1 over RP equal to R1, R2, R1 plus R2. So RP is equal to R1, R2 over R1 plus R2. Now, engineers, they will write this way. They will write it as R1 parallel R2. And they will use this formula. R1 multiply R2 over R1 plus R2. So this is a shortcut. So you should try to learn how to use it. Another thing I want you to remember is if two resistors that are connected in series, say 1 ohm, 2 ohm, because you add them together, so the equivalent resistance should be bigger than either R1 or R2. If you have two resistors, say 1 ohm, 2 ohm, if they are connected in parallel, this so-called equivalent resistor, which of course is equal to 1 times 2, 1 plus 2. So it's 2 over 3. 2 over 3 ohm. You see, this value is less than 1 and also less than 2. So what I mean is when the two resistors they are connected in series, the equivalent will always bigger than R1 and R2. When the two resistors they are connected in parallel, the equivalent resistor, in this case 2 over 3 ohm, will be less than 1 ohm or 2 ohm. Another thing I want to remember is a special case. If this is R1 and if this is R2 if they are connected in parallel, and if R1 equal to R2. Let's see what happened. The R1 parallel R2 equal to R1 R2 R1 plus R2. So this is R square, they're the same, 2R. So what I mean is this is half of the R. So for example, if this is 10 ohm, if this is 10 ohm, if they're equal, their equivalent resistance here, I can immediately tell this is 5 ohm. Okay, now let's look at how to do this question. Now the best way is try to find resistors that are connected in parallel first and try to break it down step by step. Can you see these two resistors? They are connected in parallel. So I will say I will withdraw this one and this will become. Now it's always good to withdraw your diagram. This is R5, R2. Now you are going to replace these two resistors R3 and 4 with one resistor. We call it equivalent. And we know this time this is half of 30 ohm. So this will be 15 ohm. Okay, R5 is 45 ohm. And this is also 35 ohm. Now you can see these two resistors here, they are connected in series. So I'm going to redraw the circuit again, and this is R1, this is 30 ohm, and this one is 45 ohm. Combine R2 and the 15, so this is again 45 ohm. So now you have these two resistors connected in parallel. So this circuit should be able to reduce it to 30 ohm and two resistors connected in parallel. So this is half. This is 22.5 ohm. Now you connect these two in series, so your final resistor has a value of 52.5 ohm. We can try see if we can write down one equation to simplify everything. Let's see. So we do step by step. R3 and R4, they're parallel. So R3 parallel R4. And then these two parallel resistors, they're connected in series of R2. So they're connected in series. Now, the overall resistor, this resistor is connected in parallel of R5. So this is what we have. This now connected in series of R1. So you can write a computer program and calculate the equivalent resistance of this particular circuit. Here we can see R2 and R3 are in parallel. So R2 parallel R3, and the value is equal to R2 R3, R2 plus R3, and you will find this equal to 1.2 kilo ohm. Now your circuit can be reduced as a potential divider. This is R1 and this is R2 parallel R3, and so this is V1 and this is 18 volt. Now if we want to find the V1, we can write immediately V1 is proportional to 18 volts, and the proportional constant related to the resistors. The denominator is R1 and this one is 1k ohm. R2 parallel to R3 is 1.2k ohm. 1k plus 1.2k. We want to get the voltage across R1, so the numerator is the R1, and you should get 8.18 volt. The current passing through R1, I1, is equal to V1 over R1. So it's 8.18 volt divided by 1k ohm, or 1.18 milliamp. We know now the current here is 1.18 milliamp. We can call this one I1. It's split into I2 and I3. So we can use the current division rule to find out I2 passes through R2. It means I2, beg your pardon, this is I3. So I2 passes R2. So we can write I2, which is proportional to I1. And the proportional constant, this is R2 plus R3. However, it is R3 affect the current through R2. So this will be R3. This is the rule for current division. And this one is 3k. This is 2k plus 3k. I1 is 1.18 milliamp. So you can find this roughly equal to 4.91 milliamp. Now you can similarly write down the value for I3. So I put it here. I3 is proportional to I1, and the denominator is R2 plus R3. But this time, the I3 here, I3, which is the R2 affect the I3. So I put the R2 here. And this is 2k, 2k plus 3k, I1, and you will find this is equal to 3.27 milliamp. You can double check. I1 should equal to I2 plus I3. First, we find R2 and R3, they are connected in series. So this circuit can be drawn like this. R1, and I call this R23. This is equal to 100 ohm, and R1 equal to 50 ohm. This is I0, I2, and I1. So I1 is proportional to I0, and the proportional constant is equal to R1 plus R23 And remember, when the current speeds, it is the opposite side of the resistor affect the I1. So it means it's proportional to R23. This become 100. 50 plus 100. This is 60 milliamp. And you will get 40 milliamp. This is I1. I2 can be calculated from I0 minus I1. So this is 60 milliamp minus 40 milliamp equal to 20 milliamp. V1 is the voltage across R1 and is equal to I1 R1. I1 is equal to 40 milliamp. This is 50 ohm. So this is 2 volts.